Electrolysis or electrolytic cells. We have defined a voltaic cell as something that converts chemical energy into electrical energy. It is spontaneous, which we know because two ways we know this. We have a positive cell potential, and on our data booklet, we know that the OA falls above the RA on the table. That's how we know that it's going to be spontaneous. We have other cells and for other uses where we have to force the electrons from the strongest reducing agent to the strongest oxidizing agent, and we call this an electrolytic cell. It is essentially the reverse, or can be the reverse, of a voltaic cell. So a voltaic cell turns reactants into products and electrical energy. An electrolytic cell turns reactants plus electrical energy into products. Yeah, I know it's not. So what we have here is the opposite. Voltaic cells turns chemical energy into electrical. An electrolytic cell turns electrical energy into chemical energy. And we all carry one, or I carry one in my pocket just about full time. This is both a voltaic cell when it's working, and when I plug in it at night, it's an electrolytic cell. Here's another example of an electrolytic cell, is a decomposition of water, where this is one of the ways that we can grab hydrogen for hydrogen fuel cells if we ever get around to putting the infrastructure in to put hydrogen batteries. We must add 285 kilojoules of electrical energy to break water apart into its component hydrogen and oxygen. There are many, many others. This is just one example. So the water is supplied, the energy is supplied to force this reaction uphill. So a voltaic cell is an exothermic reaction because it gives off electrical energy. The energy it gives off is electrical. So this is the potential energy diagram for a voltaic cell, where this comes off in electrical energy. And here we must add electrical energy to get this system to work. Now the products have more energy stored than the reactants did in an electrolytic cell. The only way that we can force that is use a battery or some type of an electron pump or power supply. Okay. And it is the electron energy or the power supply that causes the transfer, not going downhill. We have to force it uphill. In an electrolytic cell, once we remove it, the transfer of electrons stops. The only way the transfer of electrons stop in a voltaic cell is you break the circuit. Okay, NiCad battery. I really should update this to a lithium ion or lithium polymer battery. Nickel cadmium battery. I don't know if your parents if you ever saw your parents, or if they got a big old phone about like that. 95, 96 is about the time it was coming out. The huge batteries. But as a battery, this is the order that it happens. Okay, the cathode is the nickel, or this one with water, and the cadmium is the anode. When you force it backwards, okay, when you force the stuff backwards, you have an electron gain here. So you have the backwards reaction happen. And the only way I do that is plugging it into a power supply or the wall, etc. Now, Remember, you have to plug it into a DC power supply. Everything that we have is direct current. Otherwise, your battery blows up. What's the difference between DC and AC current? Anybody? DC stands for direct current. The electrons always flow in one direction. AC, they alternate every 1/60th of a second. The electrons go back and forth like that. So the current is changing direction each 60th of a second. The difference between voltaic and electrolytic cells is two things. That's it. One is spontaneous, one is not. One has a positive standard cell potential, one does not. So everything else is the same. The flow of electrons is from the anode to the cathode. It's forced in an electrolytic cell, but it's still from the anode to the cathode. The strongest oxidizing agent is the cathode, or is at the cathode. The strongest reducing agent is at the anode. All of those are the same. Okay? Ion movement is the same. So nothing that we have talked about before is going to change other than where our OA and our RA are in relationship to each other on your table of half reactions. In other words, the OA is not going to be strong enough to rip the electrons off the anode or off the RA itself. Now, I'm going to do the exact same process for this. Oh, he's in trouble again. No. This is Lowy was in here before. No. Now he's in trouble.
First I'm stupid.
Okay, we have a solution of potassium iodide, and we're going to run electricity through it. What's the reaction that has to take place? Well, this is our, that is an OA, that is an RA, that is an OA, and an RA. Please tell me which one is the strongest oxidizing agent and the strongest reducing agent out of those four options. Sorry, bugging teachers gets it. So potassium ion is way down here. This is why we have to remember that water is an OS or an OA and an RA. We have iodide ions up here, and the water, oh lovely, I'm going to move, and the water is above it. Okay, so the water is the strongest oxidizing agent. The iodide is the strongest reducing agent. Now, off the top of my head, I don't remember what that damn reaction is. I believe that is correct. And then the iodide is 2 of these guys. Gives me I2 and 2 electrons. Writing is getting absolutely terrible. Okay, so there is your 5-step process. The only thing is that our OA is way down here and our RA is way up there. So this is a non-spontaneous reaction. So this OA here and RA up here, that's one way of figuring out that it's not spontaneous. So, Sean, what reaction is happening at the cathode? Looking at my half reactions, is it the water reacting or the iodine reacting? Cathode. Cathode must have electrons there. This is our cathode half reaction. This is my anode half reaction. Again, the cathode is at the strongest oxidizing agent. The anode is at, or usually, the strongest reducing agent. It isn't in this case. Okay, so the electrons would flow. We would have to force the electrons from that to this one. Now, in this case, this cell is going to look basically like that. Instead of the 2 cells that we had before, the 2 half cells we had before, we're just going to put the cathode and the anode in one solution, connect it to a power supply. That's one way of writing a power supply or battery. And we're going to have reactions. And I'm going to force, in this case, I'm going to have to force the electrons. Doesn't really matter which way, they can flip. Force them that way. I'm going to have water reacting here and the iodine reacting there. Notice what will happen. At the cathode, you will have hydrogen gas being formed and hydroxide ions being formed. Cathode half reaction. So what are you going to observe? You're going to observe bubbles. And you can observe that the pH around the cathode gets higher because you're getting more basic. You're creating that. So you would have if you were to use test with a pH strip or a litmus paper, your pH strip would turn blue. You would have a solid being formed at the anode. Now, the other way that we can tell that this is a non-spontaneous reaction, still we're going to do the cathode minus the anode. Negatives, I have no clue what that is. Negative 0.83 and My iodine is up there somewhere. Positive 0.454. Okay, so my cathode is my water, my anode is my iodide. Just reading them off, I end up with a negative 1.37 volts. Now, terminology that we're going to use for that is the minimum cell voltage, or the minimum voltage that needs to be applied to this system to get the electrons across. If I apply a 1 volt difference to the cathode and the anode, that's not enough energy to add the system, or to force the electrons from top to bottom, from the anode to the cathode. So when I ask you for the minimum cell potential, I'm asking you for the negative version of this. Okay. Does that make sense to you? Okay. Now this isn't under standard conditions, but it gives us an approximation. We must add a minimum of the 1.37 volts across to get that to work. Yes, I will go on to the next lesson tomorrow. Is there anything that you need to? Now, lots of things that we use electrolytic cells for. Batteries being the biggest one that we have because they operate when we charge them. However, electrolytic cells are used to coat things. I'm going to guess at least some of you have electroplated jewelry at home. Basically, underneath the silver color or the gold color is a less expensive metal, and we electroplate silver or gold onto that metal. Now that's one of the things we do, but more often what we're going to use that electroplating for is protection. Okay. Why do I not care if the silver on or the nickel on my bumper of my car corrodes, or in the frame of my car corrodes instead of the steel? Now, the steel is the one providing structural support. That thing that we have south of town, I really wish they would have electroplated, well, probably a little small, it was 50 years ago, but if they had electroplated the girders, it wouldn't rust as bad at the bridge, because we would lose the nickel from the electroplating instead of the steel, which is more important than the nickel is, or sorry, the steel is more than the nickel. If you have a boat, you'll have the propeller electroplated in aluminum, usually. So you have lots of time today. You have these questions, and then you have questions 2 and 4 on the assignment. So when you are creating a voltaic cell, it's essentially one container, 2 electrodes, a power supply, and a solution inside.